jumlah yang joinnya ada. Sudah ada 32 orang.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. On behalf of the committee, I would like to welcome you all to the third Southeast Asian Conference on Geophysics. It is a biannual conference held by Geophysical Engineering Department of ITB since 2016. And right now we are entering the third panel discussion entitled The Open Forum in Applied Geophysics. We are very lucky this morning that we have three distinguished speakers, Professor Wawan Gunawan Abdul Qadir from Institut Teknologi of Bandung, and Professor Satria Bijaksana from Institut Teknologi Bandung, and Dr. Erding Saigin from CS Aero Australia. Each presenter will deliver their talk in 20 minutes, and then will be continued by 10 minutes of question and discussion. So for those participants who would like to raise questions to the invited speakers, please write down your question in the chat forum, or you can also send it directly to me, and I will write the question by the end of the presentation. Okay, for the first, I would like to give the time for Pak Wawan to give the talk. Pak Wawan is a professor at ITB since 2000. He has served as the chairman of the Institute for Research and Community Service at ITB. He had also served as a vice rector for ITB twice in 2010 until 2015, and then later on in 2015 until 2020. He is also the head of Indonesia Center of Excellence for CCS and CCUS, and he had a lot of international research experience with a partner from Japan, namely pilot study carbon on sequestration of monitoring in Guni area, and also in urban security engineering in megacities from 2008 to 2012, and also program on disaster resilient countries between 2012 and 2014. So without further ado, I would like to give the screen and also the time to Professor Wawan Gunawan Abdul Qadir to give his presentation in about 20 minutes. Please,
thank you. Okay, thank you to Pak David for your arranging in this nice discussion, and then also to all of you to attend the third Southeast Asian Conference on Geophysics, especially in the subtopic about applied geophysics. So now I would like to share my screen first. Hopefully already seen by all of you.
Yes,
okay. Okay, yeah. Thank you, Pak. And then in this opportunity, actually, I would like to present about the utilizing the improvement of gravimeter resolution and its application for near surface geological problem. And okay, so first slide, I would like to introduce about the resolution of gravimeter. And we know that the resolution of the gravimeters can be increased by averaging sample in the longer period. But there is also the fundamental characteristic of gravimeter the accuracy of the single measurement and also from the sampling rate. So this is the equation relating with the resolution, in which the resolution is equal to single measurement of resolution divided by square root number of sample. And then if we measure the gravimeter in the field, actually we will have the display of the unit in gal, in which 1 gal is equal 1 centimeter per second square. And also in common, actually, especially in exploration geophysics, the unit of gravity is in the milligal. 1 milligal is equal with the 10 power minus 5 meter per second square. And then in much more detail and in the small scale, and then for near surface geophysics, so the unit in microgal, 1 microgal is equal 10 power minus 8 meter per second square. And then also we have another definition actually with the resolution, especially in the signal processing. If you would like to convert the analog data to be digital data, we will face with this equation. The equation given by R is equal minus 20 log delta A divided by A. The unit is in decibel, in which the delta A is smallest reading unit of gravimeter, and then the A is our target of the gravity anomaly. And then this is very interesting relating with the resolution, in which in 2006, Virtanen et al., with his experiment, he found that the superconductor gravimeter achieve sensitivity until 10 power minus 11 meter per second square, or it is 1 nanogal. It's approximately actually 1 trillion, or 10 power minus 12 of the Earth surface gravity. This is a very, very high resolution. Let's we go to the next slide. And then, so now we see about the gravimeter for the subsurface geological survey. For this one, actually, we usually use two kinds of gravimeter. The first here is the relative gravimeter. As example, this is a Simtrack autograph CD5. And then the second, absolute gravimeter. In this case, I give an example, A10 absolute gravimeter. Both of gravimeter, relative and absolute gravimeter, actually has the reading scale until 1 microgal, or 0.001 milligal. And then also, this is a very nice result relating with the survey repeatability, in which year by year, the result of repeatability going better and better. Started in 1998, actually the repeatability or the standard deviation is around 26 microgal. And then in 2000, we have 12 microgal, but after 2002, I think the repeatability getting better, it is around 4 microgal only. And then, so let's go to the gravity anomaly on the station. In common, actually, we use the gravity anomaly in the complete Hughes anomaly. S is the station, and then this is illustration how to derive the complete Hughes anomaly. There is some correction actually, the first free air correction, the second Hughes correction, and terrain correction. For this deriving of the complete Hughes anomaly, all of the correction actually depend on the elevation and topographic map. For instance, that in free air correction here, free air correction given by this equation, and then depend on the elevation of the station. For instance, if we have deviation of the elevation each around 1 meter, for example, here, so we will have accuracy of the anomaly is only 308 microgal. And this is quite high compared to the resolution of the gravimeter itself. So if you would like to have accuracy of the Hughes anomaly until plus minus 30 microgal, so we will need topographic map with 25 to 50 meter grid size, and then less than 3 centimeter elevation error. I know this is not a simple thing to get this data. And so go to the next slide here. And we know that a lot of researchers actually conducted development of the method. One, for example, here, some researchers try to define new calculation of gravimeter, or gravity anomaly, sorry. And then it could be improvement in pre-air correction, Bugge correction, and timing correction. But actually, this development still need a high accuracy on topographic map and its elevation. For instance, this illustration we can see here, the Bugge correction and terrain correction put together in the 3D topographic model. So of course, this 3D topographic model will depend on the topographic map and its elevation. And the second anomaly, this is, we can say that another kind of gravity anomaly, such as time-lapse anomaly and then gradient anomaly. It means that we measure directly in the field for vertical and horizontal gradient and etc. But the important thing in this case that we don't need pre-air correction, Bugge correction, and terrain correction anymore. It means that it fully depends on the gravimeter resolution. So we can optimize the resolution of gravimeter itself. And then we go to the example. Actually, in this case, I show you two examples, how to optimize and then how to do the gravity survey with the high resolution relating with the gravimeter itself. The first, we'll give the example as the combined vertical gradient and residual Bugge anomaly, and then its application for groundwater aquifer compaction. In this case, I take an example in the southern part of Bandung City, because we know that the southern part of Bandung City has a quite high subsidence, and then also a lot of housing and then industry use the groundwater in that area. This is an illustration of the tripod of tower for vertical gradient determination based on Butler in 1984. And then also, if you would like to calculate the gradient, there is two opportunities. First, using linear function of height, and the second one can use quadratic function of height based on the Sapo et al. In 2003. This is an example. We have the tower actually, and then we will have three positions of gravity measurement. The first in the bottom here, and then second in the middle, and then the last one in the top of the tower actually. So from three gravity measurement, we will have two conditions. The first, if we use two measurement position of the measurement only, so we will have equation like this to calculate the gradient vertical. And then second one, if we use three measurement position, so we will have this equation to have the gradient vertical. And we go to data in the field in the southern part of Bandung. This is our area, the southern part of Bandung, geologically covered by Kosambi formation that dominated by shale and sandy shale lithology. And then in the right side here is the distribution of gravity station, quite nice distribution actually, with the space around 300 until 400 meters. And then in the left side, in the bottom here, we have the subsidence map in this area, derived from MVSAT ASAR. by G et al. In 2014. The red area here saw very high subsidence with the rates around minus 135 millimeter per year. And then in the right map here, in the bottom right side here, we have the groundwater conservation map. And then the red area here show that the alluvial aquifer damages already in this area because a lot of groundwater pumping in this area by housing and industry and etc. And then let me see the data itself. This is in the left side is the residual Brugge gravity anomaly of the area. This residual derived using high pass filter with the wavelength less than 2.5 kilometer. And then the right side is the gradient vertical anomaly. From both of the anomaly, actually, we can go much more deeper to see the very nice and then interested area, actually. The first in the A area here, and then the second in B area. From the residual gravity anomaly, we have quite high in the A area, but a little bit low in the B area. But in another side, in contrary, actually, for the gradient vertical, both of the area is high gradient vertical anomaly, even in the A area and then in the B area as well. And based on this one, so we would like to make some interpretation and analysis relating with the subsurface. Let's go to the next slide. This is the top one. This is the A area. The left and the right top one is the A area, and the bottom is the B area, left and right here. And then let me see for the first A area here. Here we have the subsurface model like this, and then there is good matching between residual, observed, and the calculate. This is a very, very nice matching here. But there is still quite high discrepancy between calculated and observed for the gradient vertical, especially in this area. And then also based on the well data, actually, we have information that the lithology that give by yellow color with the contrast density 0 gram per centimeter cube. It means this is the reference of the density in this area is only is more than 250 meter actually. But in this case, we have the model less than 100 meter. So based on this situation, the first from the gradient vertical discrepancy and then also from the position of the lithology given by yellow color. So we have to go to the new subsurface model. In this new subsurface model, we put the high density in this position with the density contrast plus 0.2 gram per centimeter cube. And then also we mix much more deeper for the yellow color in this position. So finally, we have good matching for the residual gravity anomaly and then for the gradient vertical as well. And then we go to the B area. This is the subsurface model for the B area. And then also here we have good matching for the residual gravity anomaly. In this here, calculated and observed very, very nice matching. But this is really crazy, I think, because we can see that the gradient vertical observed like this, while the calculated in the contrary. So this is really, really very high discrepancy between gradient vertical observed and calculated. So based on this one, we go to the second model. So with this situation, and then we put the high density in this position with the density contrast around 0.1 gram per centimeter cube. And finally, we get that the matching very nice for both of the anomaly, residual gravity anomaly, and for the gradient vertical as well. So from this result, we can have a conclusion actually that because we know that this area has a subsidence quite high, more than 100 millimeter per year, and then the high pumping rate also. So we can get an interpretation here that it could be as the compaction in the alluvial aquifer. Let's go to the second example. The second example is about time-lapse microgravity interpretation using 1D forward modeling of the water table changes, compaction, and subsidence due to groundwater pumping activity in Bandung city area. This is at the same location actually with the previous one, and then the aquifer is the unconfined alluvial aquifer. And let's go to the next slide here. We can see that the flow chart of the forward modeling like this. The input for the forward modeling, we have 8 parameters. The first, rock density, and then pumping rate and effective porosity, fluid density, aquifer thickness, specific storage, and the hydraulic conductivity. From 8 parameters, actually there is 2 kinds of parameters. The first kind parameter is the static parameter, such as rock density, aquifer thickness, and etc. And then the second parameter is dynamic parameter related with the pumping rate and then hydraulic conductivity, and etc. And from this input parameter, we calculate the time-lapse macrogravity and supported actually by the groundwater table simulation, compaction calculation process, and then subsidence calculation. So finally, from the time-lapse microgravity calculation, we will compare with the data from the field, time-lapse, water table, and then subsidence as well. If the fitting is not good enough, so we go to modification process, and then we put the new parameter, and then we calculate again for the time-lapse microgravity. And finally, if we get the good fitting between calculation and field data, so finally we will have the subsurface model. So let's go to the field data here. This is the time-lapse microgravity observed from 2015 until 2016. It means that the 1 year's period. The red color show the negative time-lapse microgravity, while for the blue color is positive time-lapse microgravity. And then let's go to this area. This is so high in the subsidence. The subsidence is around minus 130 millimeter per year. So this is a quite high subsidence in this area. So let's see to the result of the forward modeling itself. This is the result of forward modeling. We have 8 parameters. The bed or pumping rate actually is around 500 meter cube per day, and then specific storage around 1.35 times by 10 power minus 5, and then we have hydroconductivity around 1.8, and thickness 200 meter, rock density is 2,300, and then fluid density 1,000, and the last one, porosity is around 30%. And then we have good matching actually between observed and calculated, can we see in this figure. So time-lapse observed minus 131, and then calculated is minus 128, and etc. And then let's go to the pumping rate here. This is, I think, very important information for government. Based on this data, government can manage much more better in the groundwater using, especially for the area in which the high rate of, the subsidence very, very high. And then let's go to the summary. Hopefully this is 20 minutes enough. And the summary, the first is to improve accuracy of the Booker anomaly less than plus minus 10 microgram. It means that we would like to have the accuracy of the gravity anomaly or Booker anomaly in the range of gravimeter resolution. So we need high resolution of digital topography with the less than 5-meter grid size and then also less 3-centimeter elevation error. And the second, if we use the gradient vertical anomaly, so we will have the anomaly value accuracy in the range of gravimeter resolution with the reading scale 1 microgram. And then it's combined with the residual Booker anomaly, so we can minimize the ambiguity due to cellular anomaly body with high density value. This is about the static parameter actually. And then the third one, time-lapse microgravity anomaly value will have high accuracy. It means that the accuracy in the range of gravimeter resolution. And then it can be applied to identify both static parameter and also dynamic parameter. This is a key point, I think, why we need to time-lapse microgravity. And then the last one, I would like to challenge to all of us. Now here we have time-lapse 1D forward modeling for static and dynamic parameter. It can be extended actually to 2D and 3D. Hopefully we can get much more better the subsurface result relating with the static and dynamic parameters. So please, all of you, it will be challenges. Thank you so much.
Thank you, Professor Wawan Gunawan Abdul Qadir, for your very insightful presentation. Professor Wawan has show some recent development in gravimeter tools as well as application of gravity in solving several problems, not only for oil and gas reservoir exploration, but also in the problem in megacities such as groundwater aquifer compaction, subsidence due to groundwater pumping, and also the future challenge of the using of gravimeter in solving a problem related to the engineering. Okay, I have two questions actually from the audience. I will share my screen. I got one question from Badan Geologi. Given the fast development of gravimeter from 1998 to 2000 and 2002, the last is for microgal. Do you think there will be much improvement in the future, and how can we benefit from the improvement?
Yep. Okay, I can directly explain about this one. As I mentioned in my slide, actually after 2002, as we know that we have repeatability or the deviation of the gravity measurement is only 4 microgram. And then in another side, actually, we always talking about the gravity anomaly in around 1 milligal until 3 milligal. Especially if you would like to apply this survey for the oil and gas exploration, actually. It means that if we talk about the 1 milligal or more, the anomaly is 1,000 until 3,000. It's so high. And then useless, I think, if we use the high resolution of the gravimeter. Now, that the reason actually. Yeah, I remember that I worked also in the Badan Geologi actually in 20 years ago. And then in that time, the gravimeter resolution of gravimeter still low actually. But with this fact in which the accuracy or the repeatability 4 microgal only, so all of us, we can go to much more shape of the subsurface geology. much more detail. It means that with 4 microgal, we can analyze the anomaly with 10 microgal only. And then also, if we talk about 50 microgal, it's very easy, I think. So that's the challenge and then the opportunity in the future. So please, we can go to much more detail with the near surface geology with that repeatability value.
Thank you, Pak Mawan, for the answer. So we will continue to the second question. It is from the student of ITV. He's a bit shy to say his name. So in using 4D gravity to monitor the water use in the big cities, have you perhaps validated or checked the result using hydrogeology data? And also, do you think it is also applicable to other big cities? I think it will be very good to also apply to the other cities.
Yeah. Thank you so much. Very nice question. Actually, the first, yes, I think we have to compare, and then we have to support with the hydrogeology data. Have to, I think, this is very important. But if we talk about the city in Indonesia, it's not simple thing to get the data completely relating with the hydrogeology. That's another problem. But okay, I think in Bandung City, we already tried to compare with the well data, especially that get from the institution that have the data. And then the second one about the how to use or to apply in another city. Actually, in 5 or 10 years ago, we already conducted some time-lapse microgravity in the Semarang. But unfortunately, in that time, our carrying rating with the gravity meter is not good enough. So the accuracy is still low compared to today, I think. So this is opportunity for us. So please, if you have an idea to do the survey, time-lapse microgravity in another city, we talk with me. Thank you.
So it's an open discussion and also a challenge for us. Yeah. So perhaps it's an opportunity that we should take in the future. Let's go to the next presentation questions. It's also from the anonymous. Sometimes ago, I know people measure gravity time-lapse, but only with using handheld GPS. What is your opinion about it? Perhaps the accuracy of the location?
Yep. Thank you. Very good question, actually. Yes, position is the problem, actually. Position is the problem. But there is a very key point, I think, relating with the time-lapse microgravity. Actually, if we know right position, it means that, for instance, we measure in one location now, and then the next one, yes, we go back to that station, and then we make sure that the location in the same position, it is enough. And then also we have to make sure that the elevation and then position, and then it means that the gravimeter position from the ground. Also, we have to make sure the same. Everything without GPS, even without GPS, if we sure that the locations similar with previous one, this is enough. But if we have no GPS, I think that's the problem to put in the map. I think so. Yeah, still need the GPS. But if we have good GPS, good data position, and etc., it will be better.
Thank you, Pak Wawan. I think we still have one question. I think it will be the last question for this session. The last one from Professor Phil Cummins. If I understood correctly, you were able to identify where some compaction has occurred. Is it correct to infer that this is a permanent reduction in aquifer capacity? Is it possible that the studies like this can be quantify a threshold for sustainable groundwater extraction?
Yeah, thank you, Bill Cummins, for your question. This is a very challenging question, actually. Yeah, yes. Yeah, this is actually, if we have the good data, we have, the data from the hydrogeology and then pumping rate and etc. Much more good data. So it can be as the permanent reduction in aquifer capacity. And then also, I think this is can be the threshold for sustainable groundwater extraction. This is could be because actually we need to talk with the government, especially in Indonesia. There is problem actually with the subsidence and then with the pumping rate of the groundwater because there is no real data. The data is question mark actually. The data is not good enough, but with this our results, so it can be as the threshold for the sustainable groundwater extraction in the next. Hopefully, government can accept our result. Thank you.
Thank you, Professor Wawan Gunawan Abdul Qadir, for your very insightful talk and also the discussion. I would like to conclude the first session, so let's give big applause for Professor Wawan Gunawan Abdul Qadir.
Thank you.
Thank you. Next, we will move to the second presenter. We have Pak Satria Bijaksana, Professor Satria Bijaksana. He graduated from the Memorial University of Newfoundland in Canada in 1996, and then he got his professorship in 2010 in Rock Mechanism ITB. Previously he served as the chair of Global Geophysics Research Group at ITB. In the last 5 years, I see a lot of research project and also scientific publication in which I could not read it one by one. Also another notable achievement is that he is the co-chief scientist of the Tawuti drilling program. He is the fellow of the Royal Geological Society of London and also the recipient of the 2017 Best Partner of Foreign Research Award presented by the Ministry of Research Technology and Higher Education of the Republic of Indonesia. So without further ado, I would like to give the screen and also the time to Professor Satria Bijaksana. Please deliver your talk in the next 20 minutes. Please, Pak Satria. Pak Satria, can you hear me? Please unmute yourself, Pak Satria.
Houston.
Okay. Thank you, Pak Grandis. Okay. Okay. Can you hear me now?
Yes, clear.
Okay.
Satria.
Again, thank you, Pak David, for your generous introductions. Today, I'm going to provoke the member of audience. So instead of giving a talk about my field, I would like to probably spend a few minutes to provoke the audience regarding the geophysics. Okay, so we're talking about geophysics and changes, and I guess the major issue is, can we still debate about concept in geophysics, or geophysics is probably just a continuation of methods that already established? Can we still talk about things that's probably not quite common in geophysics, and probably whether we can extend the boundary of geophysics? Okay. So this is something that probably bother a lot of people, including myself. But how to, whether we could still talk about fundamental concept in geophysics. And I guess recent event says that yes, we could do it. Okay, so this is the common definitions of geophysics that I take from Wikipedia. So this is the probably common definitions of geophysics. It's probably very well defined and probably acceptable to a lot of people. But during the course of my study and also my career as a geophysicist, I had a chance to probably see some of these kind of interesting person in the geophysics, and one of them is Professor Carsten Stortvedt from University of Bergen in Norway. He's a paleomagnetist, and he's 85 years old now. I met Carsten during my when I was still a student in Canada, so he visited my university several times, and we had a good talk. And in fact, he came to ITB in 1998 during this what you call it, just after the sort of Reformation time. So this is kind of challenging for him to come to ITB. And I had the pleasure also to visit him in his hometown of Bergen in Norway. So the reason why I bring Professor Stortvedt is that even back in the early 90s, he questioned the lack of debate in geophysics. He basically described that back in the 60s or probably 70s, geophysics is an interesting subject because there are a lot of views and people are basically arguing, debating the whole concept. And it's understandable that it was when we had what we call the concept of plate tectonics back in the 60s and 70s. And not everybody really welcomed this concept of plate tectonics. Professor Stortvedt himself is not really against plate tectonics, but he challenged that we should basically explore new concepts. For him, it's kind of disappointing that back in the 90s, people just do the whole geophysics thing without basically looking for the concept. And plate tectonic, in his word, has been the grand unifying theory in geophysics. People do not talk about other concepts. And this is one of the reasons why he wrote actually 2 or 3 books about alternatives to plate tectonics. And one of them is global range tectonics. So again, he's not challenging plate tectonic as such, but he's kind of a challenge that geophysicists or geoscientists in general, geologists, should talk more about concepts. Okay, so basically expanding the boundary of our field, basically. Okay? So in that sense, I agree with him. Probably I don't really agree with his views that against plate tectonics, but I agree with him that yes, we have to talk more about concepts, and we push the boundaries of geophysics forward, basically. Okay, so let me give you some example. Back in 2008, there's a book, Handbook of Agricultural Geophysics. Normally, geophysics is probably something related to exploration, probably related to groundwater survey, etc., but not to agriculture. So this book is kind of interesting because it's point out that yes, we could apply geophysics in agriculture. Okay. And I guess myself and some people at ITB also looking seriously into probably developing this subject. Okay. So in 2005, there's a book that's kind of changing the whole thing. It's called the Essentials of Medical Geology. So basically now people look at whether there's a correlation between with the medical problems, in terms of populations, with geology. And I could say that this is the kind of book that I could share with my wife. My wife is a dentist and is specializing in public health. So this is the books that we all together. Normally, I have separate books. My wife have her own books. I have my own books, but this is the books that unite us together. Essential of medical geology. Okay, and the number of books actually about this subject, it's become growing more and more important. To the extent that now we have what's called International Medical Geology Association. It was established in 2006. And for those who probably have a chance, you could probably still go to Mexico for the conference in November. Okay, so this is something that's kind of exciting. That now we basically push our boundaries, and basically we could work together with people from other fields. Okay, so this is exciting. So I would like to share this excitement with the member of our audience. Okay, few months ago, here in Indonesia, we also have some kind of interesting discussions about whether earthquakes could be predicted. And apparently, this is I took this from the website of Gajah Mada University, that Gajah Mada University basically developed a system for earthquake detection that could predict the earthquake 3 days before it happens, based on observations of radon and also with the groundwater level. Again, I'm not the expert in this field, but I got excited that there's some initiatives. This method is probably still need to be tested, this need to be validated, but I appreciate the initiatives that yes, we basically have to try new things or think differently. Okay, so the USGS says no, earthquakes simply could not be predicted, but somebody at Gajah Mada said, okay, yes, we will try it. Okay, again, I appreciate the efforts, even though I'm not quite understand about the problem, and I could not really say that this is a valid methods or not. Okay, it's up to Pak David and other seismologists to verify whether this is true or not. Okay, but again, I appreciate the initiative. Okay, about 2 weeks ago, there's a paper that basically is kind of very surprising. This is still in press in quite a reputable journal, Science of the Total Environment. And I would like to point out why this is important, why this is interesting. You could look from the title. That is extraordinary. Okay, so basically, in short way, this relate this pandemic like a COVID things to geophysical and geological condition. When I saw this, I said, "Oh, this must be crazy." But when I look at carefully, I could see that the reasons given by the authors are kind of interesting. Okay, again, this would stimulate debate, would stimulate different opinions. When you look at the authors, okay, the authors, all of them are basically people with medical backgrounds, not geophysicists. But when you look at the title is surprisingly very close to our field, geophysics and geology. Okay, so let's see what the highlight of this paper. Okay, so the authors mentioned that there's no question that COVID-19, is basically a virus. It's spread to virus, everything. But what's interesting about their view is that they challenge the prediction, long-term predictions of this COVID pandemic. They look at the things that there's something that doesn't make sense in terms of severity and in terms of long-term predictions. For instance, It's just one of the arguments. The argument is that normally, if it's basically only germ-based theory or classical theory in pandemic thing, the severity, number of fatalities will be higher in, let's say, poor countries. But this is opposite. Okay, this is opposite. And then they said, okay, look, this will be severe if the populations age. But Japan proved the other way. Japan, despite of its aging population, probably have a fewer fatalities compared to other countries. So that's why they come with these ideas that this is basically outbreak is coupled with serpentinization associated with water dynamics, and this coupled also with magnetic anomalies, especially in Proterozoic cratons. So they located that the places where COVID fatality is severe is places that basically within the Proterozoic cratons. China, Iran, Western Europe, North America, as well as in South America. Okay, so I'm happy to see that report because Indonesia is nowhere near Proterozoic craton. So that could probably explain why the fatality rate in Indonesia is kind of lower. Okay, so this is another thing that's kind of interesting that this pandemic is coupled with dynamic in the geosphere via magnetic catalysis. In other words, this related to our magnetic field. Again, when I saw this paper for the first time, I couldn't understand how come COVID pandemic is related to geology or geophysics. But again, when you look at the thing, some of the things is kind of make sense. Again, I'm not fully support these notions because there's still something that I still try hard to understand. But I appreciate the efforts. This is what I mean by expanding the boundary of geophysics or geology for that matter. Okay. So this is the summary of their finding basically. So this is related the carbon dioxide rich water peridotite, with they call it lithospheric long wavelength magnetic anomalies. Okay, and this has happened because we have a weakened geomagnetic field. In graphical abstract, they put these pictures. Don't ask me what this is picture is all about. I'm still trying to understand this fully. Okay, but again, this is kind of interesting. This is exciting for me because then we talk about extending the boundary of geophysics. We talk about concept. Okay, so it's kind of interesting. Again, this probably would it took time. It will take time to basically proven as a good approach. But nevertheless, I appreciate the effort to find it. Okay. Now, having explained all these things here, this is how I come up with this approach. This is the research that I conducted with colleagues at ITB and also at other university. So basically, we use geophysical methods in other things, in other field that probably we never really considered before. Okay, so again, my objective in presenting this to you is that to stimulate discussions about possible applications of geophysics in the future. Okay, so basically we as a rock magnetist, we are familiar with magnetic methods, but we will do this magnetic methods in studying the what's called the nickel hyperaccumulator plants. Okay, so this is the team. Okay, that include someone from Tadulako University, Dr. Ayan Choa, and also Dr. Kartika Kirana from UNPAD. And the main investigator, Dr. Abdul Mujahid Hamdan, is currently at Araniri University in Aceh. He was a PhD student at ITB. Okay, so what are the nickel hyperaccumulators? So basically, it's kind of interesting that plants would accumulate or could accumulate metals in their tissue. In general, metals are poisonous to plants, but surprisingly, some plants could accumulate quite high proportion of metals in their tissues, and this include accumulation of nickel. If plants could accumulate more than 1,000 ppm of nickel in their tissues, then this plant will be called nickel hyperaccumulators. Okay, some of the nickel hyperaccumulator species could accumulate up to 25,000 ppm, which is 2.5% of the tissues are basically nickel. This is interesting considering that the nickel-rich soil or nickel-rich rocks in Indonesia is only 1% of nickel, but there's a plant that could accumulate 2.5% of nickels in their tissues. Okay, and we studied this nickel hyperaccumulators because it's the prospective use of nickel hyperaccumulators for phytoremediation and also phytomining. Phytoremediation is basically how to rejuvenate or rehabilitate sites with plants, while phytomining is basically mining the metals through plants, basically. And this become quite challenging in place like Indonesia. Despite of the great biodiversity of Indonesia, so far we have only a dozen species that we identified. Compared to Cuba, that has 130 species already identified, and Malaysia, 24 species. Okay, so this is something that probably not because we don't have nickel hyperaccumulators plants in Indonesia, but because we are not searching for this type of plants, basically. Okay, so why we use magnetic methods is very simple, straightforward, because nickel hyperaccumulating plants also contain iron, and in its oxide form, iron is magnetic. So we consider to use magnetic methods to basically study the nickel hyperaccumulators. So the ideas is, can magnetic methods speed up the identification of new hyperaccumulating plants? Okay, so the sample that we use are two species of well-known hyperaccumulators. One is Alisum murale, this is Alisum corsicum. This is the plants that could contain the highest amount of nickel in their tissues, in the leaves. And we also studied some natural samples from Halmahera and some samples from Southeast Sulawesi, basically. Okay, so this is the instrument that we use. This is the magnetic susceptibility meters, but we also use ICPOS and IIS for geochemical analysis. Okay, surprisingly, that the well-known nickel hyperaccumulators, the Alisum murale and the Alisum corsicum, have positive magnetic susceptibility, and the suspected nickel hyperaccumulators also have positive magnetic susceptibility. The non-nickel hyperaccumulators have negative magnetic susceptibility. This means that yes, we could identify the hyperaccumulator based on the magnetic susceptibility. If the plants have positive magnetic susceptibility, then there's likely that these plants would be hyperaccumulators. If the plants have diamagnetic or negative magnetic susceptibility, then these plants would certainly not hyperaccumulators. So that's basically the rough ideas. Okay, so we have successfully published our findings in two different journals. Okay, this is another papers. And our publication have attracted BBC to write an articles about our finding. For those who want to look at the articles at BBC, you could just type this title. Okay, it's kind of interesting. And because of the exposure at the BBC, then I've been approached by the mining company, PT Antam, who would like to test the prospect of phyto mining and phyto remediation in its concession areas in Gag Island near Papua. And we also attracted attentions of Mine ID. This is the holding company of Indonesian mining industries. Okay, so we would like to thanks the ITB and the Ministry of Research, Technology, and Higher Education, and also Asai Glass Foundation for supporting us in this endeavor. Now, this is the. I would like to close my presentation with two quotes. One from Albert St. Georgi, Hungarian biochemist who won the Nobel Prize in Physiology or Medicine in 1937, of his effort in identifying vitamin C. So basically, research is to see what everybody else has seen and to think what nobody else has thought. And I would like to conclude my presentation because I've seen there are a lot of graduate students in here. I was a grad student many years ago, and I could share your feeling, confusion, uncertainty. But don't worry. This is what Werner von Braun said. Research is what I'm doing when I don't know what I'm doing. Okay. So welcome to the club, and hopefully, with I hope that you have every success in your endeavor, and let's expand the boundary of geophysics. Thank you, Pak David.
Thank you, Professor Satria Bijaksana, for your very interesting talk. I always knew that you are somebody who always think out of the box, especially in geophysics. And I like the idea of phyto mining very much. Hopefully, in the future, we are not the gold digger anymore. We are the gold planter. Okay, so I do have 3 questions for you. I will share the screen. Oops, I'm sorry, it's too small. First. Okay, so it's the one question from students. So he asks, the new thought sometimes could provoke a debate and going viral. I mean, and students always have new idea. And if I had a new idea, do you have suggestion how to filter my new idea, whether I should share it or not?
Okay, this is a tricky question. When I was a student many years ago, it's not always easy to share the ideas. You have to formulate the ideas. You have to think first before you share it. But now you have social media. You could instantly share your ideas. And this is probably not a very good idea. You have to basically consider the ideas from every possible angles. Okay? Because there's possibility that, if you share your ideas right away, you could regret it. Okay? Because probably it's not well thought. So my suggestion for you, just wait a day or two, basically, and think of any possibility. Look at very different angles. In English, there's a term called the devil's advocate. Okay, devil's advocate. So basically, you probably need somebody who, your friend or your colleagues, who would challenge your idea before you publish it. Okay, in our professions as researchers or academicians, the devil's advocate is the reviewers, referees in the journal. They are your devil's advocate. They are the one who basically challenge the whole thing. So for Fikri, if you have ideas, just wait a day or two, think about it, ask for a friend or somebody else who could objectively basically look at your ideas and evaluate the ideas, and then probably after you seriously think about that, then you could share it.
Thank you, Professor Satria. So regarding the mechanism of the review or the publication process, we have also question from Pak Grandis, Professor Hendra Grandis. Given the mechanism of a research to be published, can it guarantee the validity of the method proposed? Since sometimes there are no limits to there are limits of things to be realized, for example, earthquake prediction and many other things.
Okay, Pak Grandis, thank you for the questions. This is kind of challenging because sometimes when it comes to publication, let's say in most situations, the editors would assign only like 2 or 3 people. There's possibility that these the two or 3 peoples would agree with what you said, okay, and probably this thing here could be published anyway. But in our professions, in science and in academics, there's always change. If you want to challenge something in publication, you could make comments. Somebody else could make comments to your publication, and I guess it is fair that everybody could say in an open forum, said objectively. Again, in your questions about predictability of earthquake, I'm not the expert. If you say that there's a limit, yes, I agree. But my best bet is to leave it to the expert. Okay, but I like the situation. I like the situation where people could basically share their what's so-called crazy ideas, and to make this scientific world become more attractive, because this is what Carsten Sorfet said. He missed the time where people could basically think differently. Okay? But again, Pak Grandis, I will leave to Pak David to basically answer whether this kind of earthquake prediction is really
Yeah.
valid.
Not specifically to Earth prediction, just as an example, but we praise too much on publication, so that sometimes by the author it can be a validity check. Yeah.
Yeah, true, Pak Grandis. But I guess there's somebody could make the validity check. But I guess it is the responsibility, a collective responsibility of community in general, to basically look at these kind of things. If I look at the history, what had been proposed by Newton was verified, probably a century later by Cavendish, for example. But Newton's responsibility is enough. He provoked, he developed a concept. The validity doesn't have to be done by the same person or the same group. It could be validated by other things. But I guess history would say is that there are many ideas that come up with probably not all of them come in journals, but some will come with a report, everything. But there's a as I mentioned, this is a collective responsibility of scientific community to test the ideas, and probably it takes a decade, probably more, to validate the thing. So again, for example, this when I come to this earthquake prediction thing, probably we could not validate this method in our lifetime, but probably somebody else 100 years from now, because I believe in 100 years there'll still be an earthquake, right, Pak David? There'll still be an earthquake in 100 years from now. So, but again, I guess it's interesting that we could share the thought, the opinions, without to a certain extent, yes, we have to validate our results, but probably long-term implications or long-term impacts of our research will be validated, will be developed by somebody else, Pak Grant.
Okay. I think that's answer Pargandi's question. We will move to the last question. It's from Friedrich. Could you please answer it very shortly, Pak Satria? So, knowing the world is progressively changing toward using renewable energy, geophysical exploration method used in oil and gas mining and other source of conventional energy, you think basically are not needed anymore in the future.
Short question, exploration geophysics will still be there because we could not be totally, independent from natural resources. So, but probably the magnitude probably would not be the same, but we still need this exploration geophysics.
Okay, so the exploration geophysics will be there, but perhaps with a different magnitude, with
different methods, different approach,
yes, different spectrum, and so on. So we will move to the new level of geophysics, perhaps, but still exploration is there. I think that's the answer from Professor Satria Bijaksana. Once again, thank you very much for your very insightful talk, Professor Satria Bijaksana. Let's give big applause to Satria.
Okay, thank you, Pak David.
Okay, we will move to our last presenters, Pak Erding. Dr. Erding Saigin, please, Pak Erding, please share your screen. Pak Erding is a senior research team leader in Commonwealth Scientific and Industrial Research Organization. He is an adjunct associate professor in Department of Physics of University of Western Australia. And his research interests mainly in imaging crust with the seismic method, computational seismology, seismic hazard, among many other. He has a long list of publications, and without further ado, I would like to give the screen and time for Dr. Erding Saigin. Please.
Thank you, Chairman. So today I would like to talk about imaging the Earth across scales with the correlation wave field. So just quickly, I'd like to acknowledge some of our co-authors and long-term collaborators from both CSIRO and external to CSIRO. But it's a pretty long list, and also the facilities that we've been using for the most of the results that I will be showing today. We heavily use the supercomputing facilities both at CSIRO and also in Perth in POSI supercomputing centers. So some of you are seismologists from the audience that I noticed. So you probably know quite well about the seismic ambient noise. It's a quite big topic, but I thought that I want to remind this again, that the source of this kind of signals, seismic ambient noise, in a very short way, it's a complex interaction of it's excited due to the complex interaction of atmosphere, ocean, and the ground. These elastic waves are mainly surface waves. Depending on the medium, it can be called Rayleigh, Low, or Schulte waves. But most importantly for us, the measurements of these kind of waves are very useful for us to make inferences about the subsurface structures. Another kind of the source that we use in Earth imaging these days are coda waves. Now, coda waves are actually quite familiar concept, and this is a typical seismogram that I'm showing. If you look at the first part of the seismogram, it's more like a quite well-determined wave field. You can think it's more like on a lake, the waves propagating in an orderly fashion. But if you look at the later part of this seismogram, you will see a train of energy. It looks pretty much random, but and again, if I follow the analogy, again on a lake or a puddle, you will see that wind-driven waves going all different directions. This kind of waves, although looks very random, actually in fact carries important information from the subsurface. And I will be talking about this, how we can exploit this part of the wave field again to make inferences about subsurface structures. Back to the concept of correlation wave field. Now, as I said, there are many seismologists who are familiar with ambient seismic noise techniques. But in general, it's a good idea to put a generalized term as correlation wave field. If you look at this cartoon on the left, you will see two stations, A and B, recording continuously the seismic or any kind of random lightning sources randomly distributed with random intensities. In fact, if you look at the actual records of this kind of interaction of the wave sources and the subsurface, you will see a random distributed signals, or in a quite chaotic signals that does not make much sense. It has been shown that just cross-correlate signals, and that's what the correlation vehicle term, you can extract the mystic. If you inject the source at the Earth at B, or wave field, it is very measurements about the travel times, or even the model these waveforms to make inference surface. Mainly, I measured mainly the information, the source, the random seismic waves, either seismic ambient noise or coda waves. And we can't think this is a single. But the key part is just to say if I have multiples of them, in this case, let's say n, I can look at all differential measurements and build a correlation wave field. If I have 10 stations, I can build the subsurface response of, let's say, I can extract just a bit less than 50 measurements. If I have 1,000 of them, I will have close to 500,000 differential measurements. It is very useful because once I have those measurements, I can build the local or correlation wave field, as I show in this example, as a function of time and distance. Again, for seismology, it's very simple to see that there are very clear surface waves and even body waves extracted with this kind of measurements. Correlation wave field, fortunately, is scale invariant. You can apply the same thing to whole Earth as well. In this particular example, people show that for whole Earth technique does work to reconstruct the correlation wave field for this sourceless seismology. And just repeating the same, it has transformed the seismology in the last 15 years. Okay, so why is this important? Briefly, I mentioned that those waveforms, once we extract these kind of waveforms, we can do modeling. This is just a cartoon showing that a tomographic reconstruction problem. If I have those measurements and travel times, I can create static images of the subsurface, of physical properties of the subsurface. An example from Australia, an old work of mine, showing the shear wave velocity both at 1 kilometer and 3 kilometers. So it's a tomographic imaging technique where the source is simply either seismic ambient noise in the ocean and Earth interaction, or coda waves. Now, I will go a bit deep into these coda waves, and I will try to give more examples of what else we can get it. This is an example from Central Australia, Warramanga array. It's a quasi-L-shaped array with 23 broadband seismic sensors. Has been operational for a very long time and continuously recording since 2000 with broadband sensors. The maximum station separation is around 25 kilometers. Now, this, because of the quality of the array, it records quite good both teleseismic and regional earthquakes. And our question here, can we get some meaningful information from the local structure, about the local structure, using these distant earthquake signals, but mainly the later part, coda waves? What I mean with that, back to our analogy, I'm not looking at the first part, which is very highly coherent. This is actually a seismic section from Southeast Indian Ridge with a magnitude of 5.4. If you look at the first part, you will see that the energy is very much similar between the array members, and that makes sense. This is what we call the invariant deterministic regime. But if you look at this later part, the coda part, this coherence simply breaks down. So the question here, can I extract a local information by just using this distant energy? The answer is yes. By creating the correlation wave field, using all the coda waves for different earthquakes, and through some binning, we can create correlation wave field which carries information from the subsurface, just in the vicinity of the array. And that's what we did. We look at all these different events and cross-correlate and create the seismic sections. This is the correlation wave field. Again, y-axis time, x-axis distance. All of a sudden, a coherent wave field starts to appear. Now, these are actually interstation body waves, not surface waves. Why they are not? Why we are certain about that? Because the apparent velocities are quite consistent with the previous active source studies, and the surface waves are normally are much slower. And again, this shows a simple hyperbolic pattern, as if you have one single source and multiple receivers in a typical seismic reflection survey. So to recap, I'm using distant earthquake energy to get local information, but with body waves. We didn't stop there. We actually look at some simple modeling as well. We look at the three-layer structure. We constructed this using previous reflection surveys and model and did some shooting to replicate, to figure out whether the travel times of these waves match. Now, the first two layers, the travel times are pretty much very similar to each other, so it's not easy to resolve it. But if you look at it, it mainly matches with the arrival of this first package. There is a quite weak event in the later parts. It's at least visible to me, and that also corresponds to this reflection from that. I mentioned at the beginning we use data since 2000. That's a pretty long time. So do we need all this data? So we asked the question, how many do we need to create this kind of wave field, to reconstruct this kind of wave field? So we did some random testing and look at randomly picked 500 earthquakes and the corresponding correlation wave field for different distance ranges from 5 to 20 kilometers, and you see that the energy is coherent pretty much all different bins, and that's very good. And the last panel is showing that even with 100 waveforms, stacked waveforms, we can get a highly similar energy corresponding to, compared to the using all the data. So in short, only a couple of hundred earthquakes is needed for a high synchronic stack. Now this was very exciting. But but this was from Australia. It's a pretty relatively narrow aperture array. Because we don't have an equivalent array, a long offset array, we look around and see this data set from Central America. It's a group at Caltech, and the collaborators did this experiment between 2005 and 2007. They put a large number of broadband and short period stations around Mexico to map the subducting slab. We only again look at the teleseismic earthquakes and cross correlation and complete the correlation wave field, and we get this local body waves. But in this case, it's actually quite coherent, starting from offsets from 120 kilometers to 300 kilometers. The benefit of that, again, we can use this energy to do local imaging beneath the array using distant energy. Okay, now I will slightly shift gears, but still talking about the coda waves. Now this time I will be analyzing the coda waves in a single station to map the deeper structure rather than the local structure. Again, a reminder, coda waves is the later part of the earthquakes, and an earlier, a seminal paper by Clairvaux in 1968 showed that this kind of energy can be translated into a pure P-wave reflectivity by just simple autocorrelation operation. Why is this important? Because I can convert this energy to P-wave reflectivity, where each of these the reflections will correspond to a response of a layer or a multiple from the layer. That's very powerful. So it's more, you can think of you have a layered earth, you put a source at the surface, and you get the reflections again at the surface. So we apply this new technique to a data set from Central Australia. Now, the technique has been around for a long time, but so far, until this work, no one managed to invert the autocorrelograms to map the structural image. Now, with this technique, we can get the P-wave velocity as a function of that, and that's what we did. This is the Central Australian stations, all available to us at that time. We applied the technique and also inverted for the structure. In this technique, in this particular work, we only use the vertical component to get the response of the Earth just beneath the station. By inverting all the results, we created pseudo 3D sections. In fact, the one on the left showing the 5 kilometer P-wave velocity slice of Australian continent. Slices that taken in this image is showing on the right panel, showing the major sedimentary basins. These are Canning Basin, Amadeus Basin, and Murray-Darling Basin, or also the Moho layers quite clearly. This was pretty exciting and got published in 2019 at JGR. For the first time, we mapped the continuous P-wave velocity structure, local P-wave velocity structure, local and deep P-wave structure using distant earthquake coda signals. That was for the vertical component, and we recently extended the technique to the radial component. What I mean with radial, we're not just using the vertical component, of course, but also we look at the horizontal components as well. The particular benefit of this approach, in a joint inversion scheme which we applied, you can constrain the problem in a way that your results will get better. The panel on the right is showing a set of synthetic studies. The first part is a conventional receiver function technique. We inverted for a non-velocity structure. And as you can see that P and SY velocity, although not far from the actual true model, still there are some biases. By just using the vertical component autocorrelation, as I introduced in the previous section, VP estimate is somehow better at deeper parts and VS, but there are some major biases in the VS. In the combination of these two, those biases got less, at least in the synthetic case. And that's what I marked compared to previous ones to just emphasize what I just introduced. Okay, so this is the extension of the technique, and we recently applied this to just a targeted campaign from Central Australia, a passive seismic array, Bilby array starting from Northern Australia, it's kind of like an inverted L shape, and we only use these stations from north to south because there is a co-located reflection line and previous receiver function studies exist. So we have a pretty good prior knowledge about this area. So our aim is to benchmark our technique. The figures on the right is showing the waveform fits and the resulting velocity models. So what we got after inverting all the stations, we created images of the structure. Now, not only we created images, we also compared that to previous techniques. Red dashed lines are the receiver function technique using earthquake signals, the deterministic part, and the brown dash part is showing the our previous technique. As you can see, both receiver function and the single component autocorrelations are mainly sensitive to the first order or the beginning of the crust, the beginning of the moho, much sensitive to the beginning of the moho rather than later parts. But our moho, as you see, it's not only it reduced that bias, but also offers much continuous profiles. And as a reminder, we don't get just VP, but also we get VS as well. In the next slide, I mentioned that there is a co-located reflection profile from the same region. This is the black line. And we again look at the reflectivity profile, the reflectivity character of this section, and also overlaid our results. In this case, black dashed lines are our results, and you can see easily that it's mainly showing the pretty much pinpointing where the reflectivity is stopping. And again, this is completely two different techniques. We are using earthquakes and the reflection profile using expensive crustal seismic sounding techniques. In short, we show that with this new technique, polar areas in fact carry so much information in somehow comparable to conventional crustal scale reflection profiles. And this work is currently under review at JGR, Solid Earth. Now I will shift gears and go to ambient seismic noise. When I introduced the correlation wave field, I believe I mentioned that A and B are working at the same time, and that's the common theme. When you do cross correlation, you correlate the records that belongs to the same time. Now there are ways to, in a conventional sense, if your A and B are operated at different times, you can't reconstruct the Green's function in between or the response of the Earth. With this new technique, we find an easier way by using some permanent station covering these two A and B, and through some wave refocusing, we managed to get meaningful physical signal between A and B, despite the fact that they were not working at the same time. This is quite important because in reality, especially places like Australia, our seismic deployments are quite patchy, and we don't have so many stations working at the same time. This is an example from the paper that we published this year, showing two different arrays, one from Western Australia, Alpex array, operated between 13 and 16, and another one from South Australia, Golar array, operated between 2008 and 2009. In the typical ambient noise tomography or typical ambient noise correlations, we cannot get physical signals. But with this new technique, we show that we can get clear surface waves with clear move-outs, and we also benchmark with some other permanent stations from the region and to check what we get is reliable or not. If you want to find more information, just please check the paper, which we also showed tomographic inversion as well. Now, I mentioned that this is important for Australia because if you look at this map showing the location of the permanent and temporary arrays, now Australia has still large gaps, but also the coverage is not that bad, especially in Southeast. But again, most of these arrays were operational at different times. With this new technique, we combine now these arrays in a meaningful way, and this image actually is showing what we managed to achieve. With the conventional ambient seismic close tomography, we get ray path as measurements close to 40,000 at this particular frequency. But with the new techniques, we can add close to 90,000 on top of it, and by combining them, doing ambient nose tomography, we are doing ambient nose tomography with close to 130,000 travel times. Now, of course, just increasing the number of travel times is not enough for getting a robust image. But if you look at the southeast of these images, both conventional versus the new one, you will see that the resolution is getting better. Not only the resolution is getting better, especially if you look at the central part of Australia, the anomalies are also have a better localization compared to the conventional. So, in short, by combining several temporary arrays, we increase the measurements, multiple folds, and improve the resolution. And this is an ongoing work. It's just showing slices where imaging the Australian crust and including from surface to lower crust with this new technique. And so far, 42 kilometers, the deepest image we managed to get, and this is a work that we are about to submit to a journal. Okay, I will again shift gears and talk about another application of the correlation wave field. Now, the two, not the one previous talk, but the talk before that with the gravity techniques was very interesting, and I think it's a good complementary result from, again, Western Australia. In this particular project, we use data from a shallow borehole from Harvey. This is Perth, where I live, and Harvey is around 100 plus kilometers just south of Perth. This geophone array was operated for around 4 years continuously and was quite close to the Indian Ocean. We cross-correlated continuously and created a reference wavelet and look at small changes between these waveforms. If we, by looking at by mapping those measurements as a function of time, and that's what we call VVV, velocity change. And please note that the y-axis is inverted. We clearly see a cyclic pattern here. In other words, during the wet season, the velocities are decreasing, and in the dry season, here the velocities are increasing. And the fourth row is showing the actual borehole water measurements. Is pretty much having a similar pattern. And the last row is showing the effect of temperature fluctuations and tidal changes. So what's happening here? During the dry season, the pores simply, the water within the pores get displaced and the shear wave velocity increases. And quite opposite, during the wet season, with the increased groundwater levels, the pores in the rock formations increases, the water content in the pores increases, therefore the velocity goes down. And that's pretty much following that. Now, this is not necessarily a new result, but what we did on top of that, it was both for very shallow words, and we also accurately model that. So this is showing this slide is showing actually the two both observational and modeling data. The first one is again the same results, showing with different colors, and the second column is showing the water borehole measurements, and third one is actually our modeling results. So what we did in this particular case, we used actual rock physics parameters, which we got it from the lab measurements, and try to model these observed velocity changes. And I have to say that with the right rock physics parameters, we show that the match is quite good. It almost is replicating what we see in the field. The benefits of this technique, we have so much seismological continuous data across the continent in Australia. So it's a great non-invasive technique to monitor the groundwater changing patterns of the groundwater across the continent. Last but not least, one of the last things, just as about our future activities. This is again Tito of Perth. Now, another big emerging field in seismology is using optical fiber acoustic sensing. In a very short term, this is a typical setup, a quite expensive interrogator unit sends its laser signal continuously and listens to reflections along this fiber cable. Any imperfections in this fiber, and which is always there, will be reflected back. During this observation time, if there is a deformation, that signal will be picked up as well. So people show that with this kind of setup, you can convert this as a very sensitive geophone array, and that's what we are planning to do. We are about to start listening to the Cyro fiber infrastructure to continuous measurements, to compare with conventional sensor technologies, and more importantly, to understand the subsurface structure of the Earth with noise and coda waves. The last slide is about, actually there was a good question about the future of the exploration geophysics, and I hope this will address that. One of the key things in the modern society is our dependence on critical metals. Therefore, that increased the exploration efforts, and as a part of that, we put, in collaboration with Phil Cummings of ANU, we put a large array in Murchison, Western Australia, to record seismic ambient noise, and not just ambient noise, but we want to invert this jointly and existing airborne EM data. Airborne EM data is very sensitive to very shallow work, cannot penetrate in the deeper part. Contrary, correlation vehicles can provide information deeper part, and we think that, this is a synthetic study by the way, we can combine these two techniques to get robust images to map the surface in a way that to guide exploration activities. Now, thank you very much for your attention.
Thank you, Pa Erding, for your very interesting talk. I know you from your work in ambient noise, especially the one in Jakarta, which attract a lot of citation and also discussion among Indonesian scientists, especially in that area. I do have 3 questions for you. I will share my screen. A second. Oops. Okay, share screen. Oops. This one. Yeah, I will start with the question from Pa Andri. Thank you, Pa Erdin. How to derive the local phase from the distant earthquake coda wave?
How to derive local phase, if any, from distant earthquake? I'm not exactly sure I got this question. Maybe I'm missing something here. Maybe Pa Andri can chime in.
Pa Andri?
Okay, Pa Erding.
Hi.
Okay, Pa David, I think that is my question.
Yes. Could you please explain more about this question, because Pa Erding could not get it actually.
Okay, thank you, Pa Erding. So, I got from your presentation, you can determine the local phases, like right? Something like PMP and SMS from distant coda wave. I'm right?
Not exactly. We are not looking at the local phases. We look at the distant earthquakes, and just purely with what we do for any major phase, we determine a time window following that major phase, provided there is no overlap from the other phase. We just look at that quite the coda regime, in other words. So we are hoping that there is no deterministic energy in that particular window.
Okay. Thank you, Pa Erding.
Actually, I have a short following question regarding the coda wave, because as we know that the coda wave will propagate in a random way. Yes. And how could you use this random propagation to image the layer?
Okay, yeah, that's a good question. I think I did not do a good job about describing what we are doing. So in my presentation, I mentioned that we do an autocorrelation operation. So the autocorrelation operation and also stacking will convert that coda waves, assuming that coda waves is quite well random, will convert that to a roughly reflectivity response, as if you have a source at the top and also receiver at the top as well.
Okay.
Yeah, it's more like a reflective response is more like a true zero offset reflection profiling, but that autocorrelation does that job. Yeah.
Autocorrelation and like a zero. Okay, thank you.
Yeah.
Okay, we will continue to the second question we have from Cindy. I think you know her. So thank you for the interesting presentation. Is there any specific processing that should be applied to obtain the C3 or asynchronous? Because she is trying to do it, but still encounter some problem.
Okay, I think we should be in touch in the. We try to document everything we do in the papers, but there are some couple of. I mean, maybe if you ask me some specific questions through email, I can be a better help. But I can only say as a general comment, stacking plays a big role. Long-term stacking plays a big role to improve the signal-to-noise ratio.
Okay, thank you, Pak Erding. So I got question from Pak Pil. So Pak Pil was particularly intrigued by the Perth Basin study showing the seasonal change of dV over V. Do you think this kind of study combined with other signals such as gravity presented by Professor Wawan Gunawan has much potential to study anthropogenic change in basin aquifers?
That's also a good question. I think the first part, there is definitely a potential to combine with gravity. For anthropogenic signals, I'm not, maybe what kind of scale Pakil is thinking about with anthropogenic changes? Is that more like a Jakarta context or maybe?
Pakil, perhaps?
Yeah, that kind of context, exactly.
Probably yes, but the key thing here will be long-term measurements. It is not very trivial to see maybe in a short-term duration to see these kind of effects. Another aspect, what we are planning, I mean, I haven't presented that, but right now we are playing around with in a carbon capture and sequestration site where we can detect this kind of effect. So that's an example for anthropogenic sense. But I can't tell you that so far we don't have a definitive result.
Yes. Okay. David, we have some additional explanation relating with Phil Collins. Is it okay?
Yes, sure.
Okay, it's good. It's good question from Phil Collins. I think that's right. We can put together with the seismic measurement as mentioned by previous presentation, and then yes, it should be in long period. So in gravity software also we have a long period measurement, and then we can put gravity in the same station with the seismic well, something like that, and then we can compare each other. So it will be very, very nice method together. Thank you.
I think it's aligned very well with the topic of this conference, the future challenge in geophysics, and I hope that it could serve as initiation of a future project between ITB as well as with Australia.
Yes,
okay.
That's right. Thank you.
That will be very great if we could do something together in the future. Actually, I do have a question. It's from myself, but I'm not working on the ambient noise tomography, but in using ambient noise tomography, I used to work with Pak Zul and also Bu Cindy, and people keep asking about the lower limit of the time required for stacking. Okay. Normally we use 1 month, and some people, I also got a question from the audience. Normally they use 1 year.
Yeah.
And people from the company, especially, they always ask how low could we go, and how low could we go, and how to check the reliability.
So this is a good question, and it's an open question. I think before determining before determining a fix, maybe coming a definitive answer, the first thing would be to do a beamforming analysis, and that will tell a lot what's happening in the general. ambient noise wave field. Let's say if you have a quite well distributed seismic wave field in a short term, I believe that one should have enough what's the name? If you have well distributed ambient noise, then there's a good chance that you don't need even 1 month of data. But even if you have, let's say, a year of data, but the noise is coming from one direction, then stacking is not going to do miracles, if you get my meaning.
I see. Okay, so it's depend on the data. We have to really check the
depending on the distribution of the ambient noise field, and beamforming is the key to do that, key to analyze that.
Okay. Thank you for your answer, and I think it will be the last of our session today. And before we close this session, I would like to invite all of you to turn on your camera, and we will have a photo session. Nizar, could you please help us to take a picture of all of the participants? Or Nizar is not here, so I will do the job. Okay, please turn on your camera. I will take the first page. 1, 2, 3. Okay, I will take another page. 1, 2, 3. And the last one. I'm sure you do not know where you are, but just pose, keep your best pose. 1, 2, 3. Okay, thank you very much for your help. Thank you once again on behalf of the committee. I would like to thank all of the invited speakers, Professor Rawan Gunawan, Abdul Qadir, Professor Satria Bijaksana, and also Dr. Erding Saigin for very insightful talk. And hopefully, as we have heard today, that it will be kind of the initiation of the future project between Indonesia, Australia, or between everybody in this room. Thank you very much.
Thank you.
You're welcome.
Thank you.
Bye.